Hello everyone, I'm Zhenghao Luo from NUDT. Today, I'm going to introduce our work, VulHawk. Next.
Yeah.
My presentation is divided into 5 parts. Code reuse is widespread in software development. A lot of codes and libraries are reused in software without security audit. A single vulnerability may spread across thousands of software. Unfortunately, with the development of IoT, the harms of code reuse are magnified in various scenarios. A lot of firmware only provide binary files, which have no source code available for security analysis. Therefore, binary code search becomes active research for vulnerability detection. Binary code search is applied to find a similar or homologous binary function in the repository. Here is a stripped binary. By the binary code search, we can quickly identify its functions, mark the vulnerable functions, and link their source code. However, firmware and software are compared with various compilation settings, which makes functions from the same source code may differ in binary format. For example, here is a code segment. Compared with different compilation settings, there are significant differences in the binary codes. This brings tough challenges to binary code search. Challenge 1 is that seeking vulnerabilities in IoT firmware requires the methods robust across architectures. The normal architectural work is not suitable for cross-architectural tasks. Different architectures have different registers and opcodes. This leads to out-of-vocabulary issues. Some NLP-based work uses normalization for instructions, but they still have overweight issues. The challenge 2 is that binaries from the same source code compared with different compilation settings have similar semantics, but different structures, which brings great challenges to binary code search. Here we define a file environment. It represents the combination of a compiler, an architecture, and an optimization. Considering above compilation settings, there are 72 file environments. If binaries are selected from any two above combinations, there are a total of 2,556 combination settings. The existing work tries to use deep learning to elevate their differences caused by file environment. And building a robust model, it may be possible to build a robust model for one or several specific scenarios. However, building a robust model against there's more than 2,000 scenarios is complicated. To solve the challenges, we propose a cross-architectural binary code search approach named VulHawk. It contains 3 components. The IRFM is to solve challenge 1, and the entropy-based adapter is to solve challenge 2. The IRFM is used to generate function semantic embeddings. It can be divided into 4 parts. The first is microcode generation. We lift binary code to an architecture-agnostic IR named microcode. It can be mitigate the differences of instruction type and allows our model to be trained on one architecture binaries and the search function on another architecture binaries. The second part is instruction simplification. We consider the used e-flags in the instructions for keeping the important semantics of the control flow. We also pun redundant instructions and perceive main semantics of binary code. The language model is to generate basic block embeddings. Our language model is based on robustness model. To generate overweight instruction semantics, we convert overweight operands into their root operand tokens. For example, string operands, we extract their common semantics and assign to their root token. During testing, if the input is in the vocabulary, we use the token embeddings of itself. If the input is overweight instructions, we use the root token embeddings instead. The first part is GCM layer. We use GCM model to integrate CFG structure and basic block embeddings to generate function embeddings. Here we consider basic block as nodes and jumps as directed edges. The GCM model aggregate label embeddings and use graph pruning to generate function embeddings. In the VulHawk, we propose entropy-based adapters to resolve the challenge 2. It's divided into 3 parts. The first part is divide and conquer strategy, giving an embedding space for matching similar functions. The same color points indicate similar functions. As function embeddings from different file environments are mixed together, the embedding space is confusing. The existing work tries to use a single model to build a robust model for the similarity problem with more than 2,000 scenarios. This is difficult. For example, the differences between compilers differ the differences between optimizations. It may be possible to build a robust model for one or several specific scenarios. However, building a robust model against more than 2,000 scenarios is complicated. To this end, we propose a divide and conquer strategy. First, we split the mixed embedding space into multiple embedding subspaces. Second, we choose one of the file environments as the intermediate file environment. Once the intermediate environment is selected, we divided the similarity problem with more than 2,000 similarity calculation scenarios into 71 sub-problems. We use adapters to transfer function embeddings from various file environments into the same file environment to keep similar functions together, which makes function similarity calculation easier. For the divide and conquer strategy, an important step is to identify the file environment. However, there's no information to direct indicate compilers and optimizations in binaries. We introduce information entropy and propose entropy-based method to identify the file environment. We found that the entropy streams from the same file environment are similar, while distinct from those from different file environments. Using entropy streams, we can identify compilers and optimizations. We input the entropy stream into a ResNet to predict the file environment. After file environment has been identified, we use an adapter layer to transfer function embeddings into the same file environment to alleviate the differences caused by different file environments. For more robust, function embeddings are not sensitive to mirror changes. It is coarse-grained for vulnerability detection and may introduce false positive, while the fine-grained methods are usually time-consuming. We propose a progressive search strategy. We first use a function embedding search to retrieve top K candidate functions and use a similarity calibration to integrate basic blocks, embeddings, strings, imported functions, and function similarity to predict the final similarity for candidate functions. In the evaluation, we use 10 popular projects and compare them use various compilation settings. In total, we obtain almost 600,000 binary functions. We identify 7 different tasks for evaluation, including cross architectures, compilers, optimization leaves, and their compilation tasks. For example, the XA task means cross architecture task. The baselines, including 7 state-of-art work, we use their original implementations and the default settings to evaluate the entropy-based adapter layer and the progressive search strategy. We implement 2 variants, VulHawk ES and VulHawk S. The experiments aim to answer the following questions. The first is, given 2 binary functions, can VulHawk determine whether they are similar? Here is the result of one-to-one comparison. Given 2 functions from different file environments, the models determine their similarity. It can be found that the AUC of VulHawk are higher than other baselines. According to the result, we can answer the question 1. VulHawk determines the similarity of 2 functions with high accuracy and ranked first in 7 tasks of one-to-one comparison. The second is, can VulHawk be used for searching one function in a large function repository? Here is the result of one-to-many search. In this experiment, given a function, the models retrieve top K candidate functions from the repository. VulHawk outperformed the other baselines and achieved the best recall at 1 of 0.879 in the mixed task. According to the result, we can answer the research question 2. VulHawk can achieve the best candidates with high accuracy in a large function repository. The third is, can VulHawk identify how many functions are similar for two binaries? Here is the result of many-to-many matching. In this experiment, given two binaries from the same code, the model is given how many functions are similar. VulHawk outperformed the other baselines, and its possibility distributions of recall and precision are more concentrated. We can answer the research question 1 or question 3. VulHawk can be used to match similar functions between two binaries, and it outperforms the state-of-art work in many-to-many matching. The last question is about detecting one-day vulnerabilities in the real world. We first built a vulnerability repository based on CVE database containing vulnerable functions and their patched functions of 12 related CVEs. The ground truths include 93 related vulnerable functions and 119 related patched functions from 20 IoT firmware images. The table shows VulHawk achieved high accuracy in the one-day vulnerability detection. We changed the threshold to analyze the impact of different threshold on one-day vulnerability detection. With the threshold decreasing, the precision of VulHawk decreases, while the recall increases. When the threshold equals 0.9, the recall and the precision achieve the best result. Here, we can answer the last question. VulHawk can distinguish vulnerable functions and their patched functions and detect one-day vulnerabilities with high performance over the baselines in the real world. Furthermore, we evaluate the file environment identification. The figure shows the accuracy and the cost time in the detection of optimization leaf and compilers. Compared with the existing work, our work is faster, more accurate, and more stable. We conduct experiments in various scenarios with different architectures, file sizes, and file types. The more red boxes represent higher accuracy. Let's give a conclusion. We propose an IRFM to resolve challenge 1, use a divide and conquer strategy, and the entropy-based adapters to resolve challenge 2. Propose a progressive search strategy to boost the performance and reduce the false positives, and implement prototype VulHawk. The evaluation shows VulHawk achieves higher performance. That's all. Thank you.
Hello, this is Derek McKee from MIT Lincoln Laboratory. Thank you for your talk. How will your system evaluate against purposefully obfuscated binaries?
Our system is aimed at to cross architectures, and for the obfuscate binaries, we didn't consider them. And for the obfuscate binaries, our instruction simplification can move redundant the instruction. For example, the OLLVM SUB option, we can remove the unused instructions and make the code assembly more like normal binaries.
Hi, thanks for your presentation. I'm Sima from USC University. My question is, I didn't understand your graph representation. Can you explain one more time what were the nodes and edges in your graph representation?
Oh, thank you for your question. It's about the graph presentation. The graph presentation is the we use the graph presentation to represent the function embeddings. first we generate the basic block embeddings according to their microcode, and we use the GCN graph GCN models to aggregate the basic block embeddings and use a graph pruning to generate a graph representation. And that is the function embeddings. And it can be represented the function semantics. And more detail can be found in our paper.